Have you ever really thought about what's going on when you're just, walking down the street or when a car zips past you on the highway? It all comes down to a few fundamental ideas about how things move. In this explainer, we're going to break down the basics of linear motion, and you'll probably find it's a lot more intuitive than it sounds. So let's start with a little brain teaser. Picture this. You run one full lap around a 400-meter track. You finish right back at the starting line. So how far have you moved? Now, you might think there's one obvious answer, but in physics, there are actually two correct answers, and understanding why is the key to our very first big concept. All right, let's solve that puzzle by talking about our first pair of ideas, distance versus displacement. The easiest way to think about this is to imagine a road trip. You've got the actual path the road takes, with all its twists and turns. But then you also have the straight line, as the crow flies from where you started to where you ended up. In physics, both of these are super important, but they tell us totally different stories. Okay, first up is distance. This one is pretty straightforward. It's the total ground you cover. It's literally what your car's odometer is tracking. Every single mile, every single kilometer, all added up. We call this a scalar quantity. It's a fancy term, but all it means is that it's just a number. It's a magnitude, but it has no direction attached to it. For instance, let's say our car drives 3 kilometers east, then turns right around and drives 4 kilometers west. The total distance is super easy, right? It's just 3 plus 4, 7 kilometers. Simple as that. But now let's look at displacement. This is where physics starts to get a little more picky. Displacement completely ignores the path you took. It only cares about one thing, the straight line distance from your start point to your end point. And this is absolutely crucial. It always includes a direction. This combo of a number and a direction is what we call a vector. So let's go back to that car trip. It went 3 kilometers east, then 4 kilometers west. The displacement is not 7 kilometers. Think about it. Where did the car actually end up? Well, it finished 1 kilometer west of where it started. And in physics, we can show that direction with a simple plus or minus sign. So if we say east is positive, then west has to be negative. That means your displacement is negative 1 kilometer. See how that little minus sign tells you everything you need to know about the final direction? And this really sums up the whole idea perfectly. Displacement is all about the net change in your position, not the journey it took to get there. So let's go back and solve our track problem. The runner's distance? Yep, 400 meters. But because they ended up exactly where they started, their displacement is a big fat 0. Okay, so we've nailed down where an object moves. Now let's start talking about how fast it gets there. The moment we add time into the mix, we get another pair of concepts that people mix up all the time, but in physics, they're worlds apart: speed and velocity. The difference between speed and velocity is basically the same as the difference between distance and displacement. Just look at the formulas. Speed is your total distance divided by time, which makes it a scalar, just a number. But velocity? Velocity is your displacement divided by time. And because displacement is a vector, that means velocity is also a vector. It has both a speed and a direction. This is exactly why your GPS cares about your velocity. It doesn't just need to know how fast you're going. It needs to know you're going in the right direction to get you to your destination. Of course, speed is rarely the same for a whole trip, and we've got different names for it. Let's stick with our car journey. When you're cruising on the highway with cruise control on, that's uniform speed. It's constant. But then you hit city traffic. All that stopping and starting means your speed is non-uniform. Anytime you glance down at your speedometer, you're seeing your instantaneous speed, your speed at that exact moment. And then, at the very end of the trip, if you take the total distance you drove and divide it by the total time it took, you've got your average speed. So we've got a handle on how to measure motion, but here's where it gets kind of trippy. How we see that motion can change completely depending on our own point of view. I mean, if you're also moving, how do you even describe how something else is moving? This is where the really cool concept of relative velocity comes into play. Relative velocity sounds complicated, but it's just the velocity of one object from the perspective of another moving object. Think about driving on the highway again. That car in the lane next to you, how fast does it seem to be moving? Well, the answer totally depends on how fast you're moving. Let's look at this situation. We've got 2 cars, both heading in the same direction. One's going 50 kilometers per hour, the other's at 30. Now, to someone standing on the side of the road, those are their speeds. But to the driver in the faster car, the slower car actually looks like it's going backwards at 20 kilometers per hour. Their relative velocity is just the difference between their two speeds. But what if they're driving towards each other? Well, in this case, you add their speeds together. From the perspective of either driver, that other car is flying towards them at a combined speed of 80 kilometers per hour. And this, right here, is why head-on collisions are so incredibly devastating. The relative velocity is just massive. So we've covered things moving at a nice, steady pace. But in the real world, things almost never move at a constant velocity forever. They speed up, they slow down, they turn corners. What do we call all that change? Well, that brings us to our final and maybe the most important concept of all, acceleration. When most of us hear the word acceleration, we think of flooring the gas pedal, right? Just speeding up. But in physics, the definition is so much bigger. Acceleration is any change in velocity. And remember what velocity is. It's a vector. It has speed and direction. So, you are accelerating if you speed up, you are accelerating if you slow down, and you are even accelerating if you're just changing direction. This table breaks it down really nicely. If your velocity is increasing, that's positive acceleration. You're speeding up. If your velocity is decreasing, that's negative acceleration, what we usually just call slowing down or braking. And here is the key. If your velocity is constant, meaning your speed and your direction are locked in and not changing, your acceleration is zero. So that car on cruise control, it only has zero acceleration if it's on a perfectly straight road. The second it starts to turn, it's accelerating. So let's wrap this all up. What are the big things to remember? First, scalars like distance and speed are just simple numbers. But vectors, that's displacement, velocity, and acceleration, they have both a number and a direction. That direction makes all the difference. And don't forget, acceleration is any change in velocity, period. It's not just about speeding up. So I'll leave you with one last thing to chew on. Imagine a satellite orbiting the Earth. It's moving at a perfectly constant speed. It never gets faster, never gets slower. So my question to you, is it accelerating? The answer is hidden in everything we just talked about, the difference between speed and velocity, and what it really means to change direction.